In today's lesson, we are going to look at negative and zero exponents. So this is just kind of a throw-in kind of lesson. You have probably looked at this before, but it doesn't hurt to kind of review this because the main focus in grade 9 would have been the your quotient rule, your product rule, and your power of a power rule. Negative and zero exponents, maybe you didn't look at too much, but you will start to look at them more, not so much in this course or in this grade, but when you're looking at powers and exponentials in grade 11. So it doesn't hurt to kind of refresh this right now, just so you do have some recollection of it, hopefully going into next year. So negative and zero exponents. So just to recall what we've looked at before, right? These are the kind of the other main power rules. These are the main three from grade 9, right? Your product rule, when you're multiplying powers, what do we do? Right? Hopefully remember, we add our exponents. So for multiplying powers with the same base, we add the exponents. So for example, 2 to the power of 2 times 2 to the power of 3, we add those exponents, and we get 2 to the power of 5. The quotient rule, when we're dividing, right, we subtract. So a to the power of m minus n. So we subtract our exponents. So the 2 to the power of 4 divided by 2 to the power of 2, we subtract. So 2 to the power of 4 minus 2, or 2 to the power of 2. And then finally, our power of a power rule, the third main one, we multiply our exponents. So m times n. So 2 to the power of 3 to the power of 3, 2 to the power of 3 times 3, or 2 to the power of 9. Right, so those are the main three rules that we would have looked at in the past. In grade 9, hopefully you kind of remember them. We're going to kind of refresh the zero exponent rule first, and then the negative exponent rule. So the zero exponent rule, we have a to the power of 0. The rule for this, anything to the power of 0 is equal to 1. You may have saw on the first, like kind of the title slide, well, what happens like if it's 0 to the power of 0, right? Because 0 to the power of anything else would be 0, but does 0 to the power of 0 equal 1? And I kind of looked it up because I was kind of curious, just in case someone asked. I think they said, or I found that they state that any 0 to the power of 0 is considered undetermined. Not undefined, but undetermined, right? Because we can't determine whether it's a 1 or a 0. Right, so I don't know if that kind of makes sense. It's kind of like that kind of theoretical math, or kind of extending it beyond kind of our purposes right now anyways, but that could be something that mathematicians look at in the future of trying to decide what is 0 to the power of 0. So the proof for how this works out to 1, well, we have 4 to the power of 3 divided by 4 to the power of 3. So if we're going to use our quotient rule, when we divide powers, we say, well, 4 to the power of 3 minus 3 equals 4 to the power of 0, and our rule states that that is 1. Now, if we're going to prove that, what is 4 to the power of 3? Right, that's just using those rules. Well, 4 to the power of 3 is 4 times 4 times 4. And if we're going to divide that by 4 to the power of 3, that's 4 times 4 times 4. Now I could go through and I could look at, okay, well, I can expand this. 4 to the power of 3, well, that's 64. 64 over 64, that is a whole fraction, or 1. Another way you could think of it is, well, if I wanted to say 4, different color, 4 times 4 times 4 over 4 times 4 times 4, right? I could actually say, okay, well, if I'm multiplying by 4 on top and I'm dividing by 4 on the bottom, they can actually cancel out. So I can cancel out on 4 on the top and the 4 on the bottom for each one. And so what's left over, there needs to be a placeholder. It can't just be nothing, right? So we have 1. or when we divide 4 divided by 4 is 1, times 4 divided by 4, which is 1, times 4 times 4 divided by 4, which is another 1. So 1 times 1 times 1, or which is 1. Negative exponent rule. Our negative exponent rule states that if we want to turn it into a positive exponent, it's going to be 1 over a to the power of n. Or in other words, we flip our exponent or our power, and the exponent becomes negative. So if we want some proof, right? So if we go through 3 to the power of 2 divided by 3 to the power of 5. So our rule states for dividing powers that we subtract exponents. So we get 3 to the power of negative 3. Right? And our rule states that this now becomes, if I want positive exponents, 1 over 3 to the power of 3, or 1 over 27. So the proof comes from, let's expand this. 3 to the power of 2 is 3 times 3, divided by 3 to the power of 5, which is 3 times 3 times 3 times 3 times 3. So I could expand this and say, okay, well, 3 to the power of 3 is 9, divided by 3 to the power of 5, which is 243. And if I reduce this, I get 1 over 27. So just by mathematically doing the calculations, it does work. Or what I could do, right, if I want to look more at kind of showing how this process works, 3 times 3 times 3 times 3 times 3. The rule states, right, or not the rule, but just mathematically, if I have the same numbers on top being multiplied and I'm multiplying by the same numbers on the bottom, I can cancel out. Keep it consistent. I can cancel out. There'd be a 1 left over on top. So 1 over 3 times 3 times 3. Or 1 over 3 to the power of 3, or 1 over 27. Right, so hopefully enough proof to realize why this rule works. And if not, right, you can just kind of say, well, that's what we're learning, that's what it is, but this is the proof behind that rule. This is why that rule exists, because of examples like this. So they've gone through and they've proven that rule. So let's just go through a couple examples. We want to write each as a power with positive exponents and then evaluate. So 2 to the power of negative 3, kind of straightforward. We said we flip it. So 1 over 2 to the power of positive 3, which becomes 1 over 8. So evaluate means to find an actual answer, find the final value. And generally speaking, if we're dealing with this, we want to leave it as a fraction. Right? I don't want you to just plug 2 to the power of negative 3 into your calculator, because chances are you are going to get a decimal number. Now, depending on your calculator, you might get the fraction, which is fine, but in other cases, it's most likely that you're going to get a decimal number, and we would rather keep the fraction. Negative 4 to the power of negative 3. So again, we flip our term, or our power, right? So we can think of it as 4 over 1. We flip that, it becomes 1 over negative 4 to the power of negative 3. I can evaluate, or not negative 3, sorry, positive 3 now. I can evaluate this, so negative 4 times negative 4 times negative 4. We get 1 over negative 64. Now just make sure you put this in brackets, right? Include the brackets when you're doing the calculation. It's very important that when you have a negative value or a negative base of your power, that you include brackets when you're entering it into your calculator. If you do not, chances are you could get the wrong answer. In this case, it wouldn't matter. You'd probably still get the same answer, but in other cases, you do want to include the brackets. C, same idea. So we have 2 different options here because we're dealing with a fraction. So there's 2 different ways you could think of this, right? So, okay, we say we flip, right? Or we flip it and it becomes a positive exponent. So it becomes 1 over a fraction, 2 to the power of 3 to the power of positive 2, which works out to, if we evaluate, 1 over 4 over 9, because that exponent of 2 applies to both parts. Now you could read this as 1 divided by 4, or let me rewrite this. 1 is a fraction divided by 4 over 9. Now how do we multiply, or how do we divide fractions? Well, we flip the second one and we multiply. So 1 multiplied by 9 over 4, which is just 9 over 4. So that's one option. And our final answer evaluated is 9 over 4. The other option is we just flip the fraction. So our other option, I should do this in purple, is I flip my fraction, so 3 over 2, and make the exponent positive. So that becomes this 2 applies to both the 3 and the 2. So we get 9 over 4, which is the same answer. So you could go the long way. You could flip it over 1, and then when we realize, oh, we're dividing a fraction, so that means that either the 9 comes up to the top, or we flip that second fraction when we were dividing and we turn it to multiplication. Or you can just flip the fraction and make the exponent positive. Lastly, 0 to the power of negative 3. So we flip it, so it becomes 1 over 0 to the power of positive 3, which is 1 over 0, which is undefined. So this one's undefined because we can't divide by 0. So we have an undefined answer, or a math error. Lastly, we're going to be looking at using some of these kind of example or kind of exponents in more of an application. So carbon-14 is a radioactive element that decays to half, or 2 to the power of negative 1, of its original amount after every 5,700 years. We want to determine the mass of 10 grams of carbon-14 after 11,400 years, and then B, 28,500 years. So what we have to do first is determine how many 5,700 year periods there are. Because this will tell us how many half-lives there are, or basically how many times we've decreased by half. So if I take 11,400 divided by 5,700, I get 2, which means 2 half-life periods. So this is just a fancy way of saying we've decreased by half twice. So what we can do then is we can take the fraction 1 over 2, bring it to the power of 2, and we multiply it by 10. So that's just a fancy way of doing. If I rewrite it, I could say, okay, I have 10 grams. I multiply it by a half to get half the amount. And then I multiply it by a half again to get half of that amount. And then again, just the easier way of writing it is I can just say 10 times 1 over 2 squared. This becomes 10 times 1 over 4, which works out to 2.5 grams remaining. So after 1,400 years, there's still going to be 2.5 grams of carbon-14 remaining. Right. So again, this idea of decay, or radioactive decay as it's known as, kind of shows why radioactive material is so dangerous, because it remains around for such a long time. B, going to be the same idea. We have to determine how many half-life periods there are. So if I do 28,500 and I divide it by 5,700, we get 5. So this means that there are 5 half-lives, or half-life periods. So now we can do 10 times, instead of times a half to get, and then times a half again, times half again, times half again, and so on, we can just say 10 times 1 over 2, or half to the power of 5. We get 10 times 1 over 32. And we get 0.3125 grams remaining. So even after 28,500 years, there's still going to be a little bit amount of this radioactive element left over. So again, shows the danger of some of these radioactive materials because of how long they can stick around or stay radioactive. So again, this is kind of like an add-on lesson, a throw-in lesson, looking at negative and zero exponents. Hopefully this was reviewed because you did look at this in grade 9. But again, it doesn't hurt for a refresher because this will become more important next year. So it's kind of like a bridge of learning, so you can kind of get a little bit of a refresher so that it hasn't been 2 years since you've seen exponent laws or these power rules.